That rock you're holding, it's a time capsule from a world-ending event. We're going to go down deep into the Earth's crust to find these fossilized climate disasters. They're hidden in the rock layers, and by the end, you'll see the planet's history differently. You'll understand what these stone archives are saying and why it matters for us now. So, how did they do it? Geologists found the chemical signature of an asteroid, a city-sized asteroid, in a thin layer of clay. Just a thin layer, and then there's the planet covered in ice, from pole to equator. What does that teach us about our own climate? It's all there. This is the story. Earth writing its own autobiography. In stone, it recorded every apocalypse, suffocating oceans, volcanic winters. These aren't just ancient stories. They're a library of warnings written in minerals and isotopes, waiting. So what are the rocks under our feet trying to tell us? They're trying to tell us. 252 million years ago, the planet almost ended. The experiment with complex life nearly failed. That event is called the Great Dying. And that name fits. Over 90% of marine species just vanished. On land, the forests turned to dust. This wasn't a quick disaster. It was a slow unraveling of the systems that support life. The entire story is pressed between two layers of stone. That boundary between the Permian and the Triassic is one of the most significant pages in Earth's story. In a cliff face, it's often just a thin, dark stripe. To most people, it looks like a layer of dirt, but to a scientist, that dark line is a crime scene. It's rich in soot and strange minerals. It's an ashen residue from a world on fire. Paleoclimatologists drill into these layers. They find bizarre signals. One of the most haunting is the fungal spike. Right at the boundary, the fossil pollen from forests disappears. It's replaced by a massive bloom of fungal spores. The story is stark. The world's great forests had fallen. The decomposers, the organisms that thrive on decay, briefly became the dominant form of life on land. They ruled over a landscape of fallen giants. But what could cause that? The rocks point to one event. A monstrous event centered in what's now Siberia. There, the planet's crust split apart. The eruptions were so vast they're hard to comprehend. This wasn't a single volcano. It was a flood of lava covering an area the size of a continent. For hundreds of thousands of years, these fissures belched carbon dioxide and methane into the air. The rock record becomes a forensic report. First, you see the signature of sudden, extreme warming. Isotopes of carbon show a wild, erratic swing in the layers. That indicates a massive, rapid injection of greenhouse gases. Then, the oceans begin to suffocate. The beautiful layers of limestone made from sea creature shells, they thin and dissolve. That's the mark of ocean acidification. The seas absorbed too much carbon dioxide and became corrosive. In deeper water rocks, you find evidence of anoxia, a complete lack of oxygen. These were dead zones. Anything that couldn't escape just perished. And finally, a smoking gun. Traces of the element mercury, carried globally by the volcanic gases, found in high concentrations in that same dark boundary layer that directly links the Siberian eruptions to the global die-off. One of the best places to read this story is in Meishan, China. It's the global reference point for this extinction. Scientists come from all over to study the sequence. You can run a finger along the rock, move through millions of years of history, and feel the precise moment where everything changed. The layer is there. Tangible and real. It makes you wonder about deep time, about the fragility of the web that sustains life. An ecosystem that took tens of millions of years to build was dismantled in a geological instant. This layer of rock is the ultimate testament to that loss, a stark reminder written in stone of how quickly a world can turn. That thin, dark line in the rocks. It's a tombstone, but Earth's stone library. It holds records of different kinds of disasters. 66 million years ago, the story wasn't written from within. It came from the sky, a moment of cosmic violence. It reset the course of life. The evidence is a layer of clay, no thicker than your finger, found in rocks all over the world. That's the Cretaceous-Paleogene boundary, and it held a secret, one that baffled scientists for decades. In the late 1970s, a physicist named Luis Alvarez and his son Walter, a geologist, they were studying this layer in Italy. They wanted to know how fast the dinosaurs disappeared. Was it a slow fade or a sudden end? They used a sensitive instrument. It could detect trace elements. And they found something. The clay was wildly rich in iridium. Iridium is incredibly rare in Earth's crust, but it's common in asteroids, in comets. The Alvarez team proposed a radical idea. This global iridium spike was asteroid dust, spread across the planet by the force of an impact. The scientific community was skeptical. Where was the crater? The evidence seemed thin, too delicate for such a cataclysmic idea, but then the rocks began to speak more clearly. Geologists found other signatures in that same clay. One was shocked quartz, tiny grains of quartz. Under a microscope, they show a pattern of parallel lines. That pattern only forms under pressures greater than any volcano. It's the fingerprint of a violent impact. Another signature was tektites, tiny glass beads, formed when rock is vaporized by the heat of an impact. It's flung into the upper atmosphere. Then it falls back as a rain of molten glass. Finding these in the same layer from New Zealand to North America, it painted a picture, a single, globally synchronizing event. The narrative became clear. An object maybe 10 kilometers wide struck the Yucatán Peninsula. The energy released was billions of times greater than the Hiroshima bomb. The immediate effects were local hellfire, but the rocks tell us the true killers were the global aftermath. The impact threw so much dust and soot into the stratosphere it blotted out the sun worldwide. That's the impact winter. Photosynthesis stopped, food chains collapsed from the bottom up. Layers of soot in the clay suggest global wildfires raged. The vaporized rock also released sulfur. It mixed with water vapor to fall as corrosive acid rain, poisoning the land and seas. The ultimate proof lay hidden for millions of years. Beneath the jungles and waters of the Yucatán, the Chicxulub crater, buried under a kilometer of younger limestone. Its outline was first revealed by subtle variations in gravity maps. Drill cores brought up samples from the crater's peak ring, and there scientists found granite. Granite belongs deep in the crust. The impact was so violent it lifted the basement rock of the continent. It splashed it upward before it melted and settled back down. Those cores contain a frozen moment, rock that was melted in an instant, 66 million years ago. Holding a piece of it is to hold a fragment of that exact day. It makes you reflect. For over 150 million years, dinosaurs ruled. Their world was stable, lush, diverse, and then, in a geological flash, it was over, reset by a random visitor from space. The KPG boundary is that reminder. Our planet's story is written not just by its own internal forces, but by the chaotic environment of the solar system. It records a day when the sky fell, and it asks a quiet question. In a universe full of moving rocks, how much of our future is written in the same stone? Earth's rock record tells another story, not of a world on fire, but one frozen solid, a planet locked in ice, that Snowball Earth. The evidence starts with a puzzle. On different continents, places like Namibia's deserts, Australia's outback, you find ancient rocks with clear glacial marks, scratched bedrock, chaotic boulder piles called tillites. But the fossils say these were tropical places near the equator. So how could glaciers exist at sea level in the tropics? The only answer, even if it seemed impossible, is that they did. Because the whole planet was frozen, scientists like Paul Hoffman put it together. In Namibia, he saw a striking sequence. At the bottom, those glacial deposits. Right on top, a sudden shift. A thick, distinct layer of limestone, a cap carbonate. That pairing is the key signature. First, a deep freeze, then a sudden, intense greenhouse. The rocks showed a planet undergoing climate whiplash. So how does a planet freeze completely? It begins with a runaway effect, the albedo effect. Albedo is just reflectivity. Ice and snow are bright white. They reflect sunlight back into space. As the planet cools and ice grows, it reflects more light, which cools the planet further, which makes more ice. It's a self-reinforcing cycle. Once ice reaches a critical point, maybe around 30 degrees latitude, the loop can become unstoppable. In a few thousand years, the entire ocean could be sealed under a kilometer of ice. The planet becomes a white marble in space, a snowball. Ocean life would have been pushed to the edge, surviving only near volcanic vents under the ice. The rocks show this. Unique iron-rich formations appear in these layers. They only form when the ocean is cut off from the air, letting dissolved iron from vents build up without rusting. But maybe the most striking evidence is in South Australia, in a formation called the Elatina. It has rhythmic, wave-like sediment layers. Scientists see those as tidal deposits. Tides in an ice-covered world. That means the ice over the oceans wasn't always a solid lid. Near the equator, it might have been a thin, slushy skin. A slush ball, not a hard snowball. Sunlight could still get through, and the moon's pull could still make the slushy ocean beneath pulse with a weak tide. So how does a snowball Earth ever thaw? The planet's own internal fire saves it. Volcanoes keep erupting. They pump carbon dioxide into the atmosphere. But with the oceans frozen, there's no rain, no weathering to pull that CO2 back down. The greenhouse gas builds up for millions of years until it's hundreds of times higher than today. Finally, the greenhouse effect overpowers the ice's reflectivity. The thaw, when it comes, is geologically instant. A super greenhouse world breaks out. And that's what the cap carbonates are. As the ice melts, weather returns violently. Torrential, acidic rains fall through the thick CO2 atmosphere. They weather the barren continents fiercely, washing huge amounts of minerals into the warming sea. The oceans, supersaturated, suddenly precipitated all out as those massive global limestone blankets. They're the chemical sigh of a planet escaping its ice. This frozen record makes you think our planet isn't inherently stable. It can tip into extremes that seem unthinkable, a global icebox, a global hothouse. And yet, it always finds a way back. The systems, stretched to their limit, eventually rebalance. The rocks that prove the snowball also prove the thaw. They're a dual record of fragility and resilience, a reminder that the climate has a memory, and its capacity for change dwarfs all of human history. The rock record shows another kind of climate disaster. It's a story of silence, an ocean holding its breath. We see it in the Jurassic, which we think of as the age of giant reptiles, but the seafloor tells a different story. There are these vast expanses of a certain rock, a dark, finely layered shale, almost oily. The most famous is the Kimmeridge clay under parts of England. To hold a piece is to hold something heavy, dense, eerily rich. This rock wasn't formed on a vibrant seafloor. It was born in a dead zone. Geologists call these oceanic anoxic events. Anoxic just means without oxygen. It's when the ocean's normal circulation breaks down. Warm surface water, heated by a greenhouse climate, gets less dense. It forms a stagnant lid, sealing off the deep. No fresh oxygen mixes down. Life on the bottom suffocates. Everything that sinks, dead plankton, organic debris, it just piles up. With no oxygen, there are no scavengers, no burrowing worms to churn it. The organic matter accumulates, layer upon pristine layer, preserved in detail. Over millions of years, that pressure cooks it into the rock we see. Sedimentologists have a practical term for these. They call them world-class source rocks. That dark, oily shale is the literal source of much of the North Sea's oil and gas. The fuel of our modern world was created in a moment of the ancient world's collapse. So what triggers the ocean to choke? The rocks point to a cascade. It often starts with a pulse of intense volcanism, like the splitting of Pangaea, that pumps carbon dioxide into the air, warming the planet. On the warmer continents, weathering increases. It washes vast amounts of nutrients into the seas, like pouring fertilizer into a pond. It causes massive plankton blooms at the surface. When those tiny organisms die, they sink and decompose, and that process itself consumes oxygen. The warm, freshened surface water refuses to sink. It seals the fate of the depths. The ocean becomes stratified, layer-caked and stagnant. The evidence is in the shale itself. Under a microscope, you see an abundance of certain plankton fossils. Cyst-forming algae that thrived in these low-oxygen surface waters, and you see a profound absence, almost no traces of burrows. A healthy seafloor is churned up, bustling. An anoxic seafloor is a still, laminated canvas, untouched for eons. One clear chapter is the Torsion oceanic anoxic event, about 183 million years ago. Its signature is found globally, from the cliffs of Yorkshire in England to rock sequences in Japan. There, scientists see a sharp, negative carbon isotope excursion in the layers. That's a geochemical way of saying the system was flooded with a huge, rapid injection of light carbon, almost certainly from volcanoes and thawing methane deposits. It's the same signal of a climate system in shock. The black shales from this event are a global tombstone for that suffocated world. It forces a quiet reflection. The land, the sea, the air, they're not separate. A volcanic rumble deep in the earth can alter the atmosphere. That changes the climate, which starves the ocean of breath. The beautiful, dark Kimmeridge clay is the physical proof of that chain. It preserves the memory of a choking biosphere, a reminder that the planet's systems are linked in the most intimate and sometimes the most devastating ways. The past has this direct warning, a sudden fever that hit the planet 56 million years ago. The rocks have a name for it, the Paleocene-Eocene thermal maximum. The PETM, it was a geological flash, a few thousand years where temperatures went up 5 to 8 degrees Celsius. That might not sound like much, but on a planetary scale, it's a radical shift. We know about it from a chemical whisper trapped in mud at the bottom of ancient seas. It's called a carbon isotope excursion. Carbon atoms come in different weights. Isotopes, plants prefer the lighter one. Methane molecules do too. Volcanic carbon is heavier, so scientists can measure the ratio, light carbon to heavy carbon in ancient sediments. And they can read the source of the carbon in the air back then. In ocean cores from around the world, in a layer from 56 million years ago, that ratio plummets. The curve on the graph dives sharply negative. It's the signature, a massive, rapid dump of light carbon into the atmosphere and the oceans. Something flooded the system. That layer in the deep sea cores is visually striking. It's often a red or dark clay layer, sandwiched between the white and gray oozes of a normal seafloor. And it's barren, devoid of these tiny, shelled fossils, foraminifera, which usually make up that ooze. The reason is simple. The ocean had absorbed so much of that extra carbon dioxide. It became corrosive, acidic. The water dissolved the shells of these creatures as they tried to form. For a time, the deep sea became a silent desert. For anything with a calcium carbonate shell, so the source of all that light carbon, the leading suspect is methane, not from the sky, from the seafloor. Miles under the ocean, in cold, high-pressure environments, methane gas gets locked into cage-like structures of water ice. methane hydrates, a frozen fuel. They're stable until the temperature rises. The theory is some initial warming, maybe from intense volcanic activity in the North Atlantic. It warmed the ocean depths just enough. And it touched off a chain reaction. The hydrates melted, releasing bubbles of potent methane. That methane rose, reached the atmosphere as an even stronger greenhouse gas than CO2. Caused more warming, which melted more hydrates, a runaway feedback loop, a climate bomb detonated from the seabed. On land, the fossil record tells a story. Life scrambling to adapt. In the Bighorn Basin of Wyoming, you can walk the Badlands and see the PETM. The rock layers change color abruptly, from the muted purples and grays of the late Paleocene. You hit a distinct, thick band, bright pink and orange sediments. This is the PETM layer. It represents a dramatic shift, soil and weathering conditions in a much warmer, wetter world. And in these colorful rocks, paleontologists find mammals. They find something strange, dwarfing early horses, ancestors no bigger than a small dog. Found in these layers at a much smaller size than their ancestors just below. In a warmer, carbon dioxide-rich world, plants can become less nutritious. One survival strategy is to get smaller, require less food. Other species, like early primates, appear here in North America for the first time. They likely migrated north from tropical regions. Following the heat, the world's climate zones were on the move, and life had to move with them or change fundamentally. This event is a precise analog. The closest thing the rock record has to a controlled experiment for rapid, carbon-driven global warming, the entire perturbation, the carbon release, the warming, the ocean acidification, and the slow recovery. It took place over about 170,000 years, a blink in deep time, but a vast span compared to human history. Yet we are now releasing carbon from fossil fuels at a rate estimated to be at least 10 times faster than during the PETM. The rocks are showing us a possible future, written in the chemistry of an ancient past. They ask a sobering question. If the planet took 170,000 years to recover from that fever, what does a rate 10 times faster mean? For the world we are creating today, 74,000 years ago, a volcano in Indonesia ended the world, Mount Toba. It didn't just erupt, it disintegrated. In one event, it put over 2,500 cubic kilometers of material into the air. To get the scale of that, picture Manhattan buried under ash. Ash more than 4 miles high, and that ash didn't just fall nearby. It made a global layer, a fingerprint. You can find these microscopic shards of volcanic glass, they're called cryptotephra, in sediment cores from the Indian Ocean floor. You can find them in ancient lake beds in East Africa, thousands of miles away. These tiny, sharp pieces are the calling cards of a super-eruption. They link one violent moment on an island to a planet-wide climate shock. The immediate killer wasn't lava, it was winter, a volcanic winter. When Toba blew, it sent huge amounts of sulfur dioxide gas up into the stratosphere. That gas mixed with water vapor and formed a haze of reflective sulfate aerosols. This wasn't a cloud that would rain out. It was a persistent global shroud. It acted like a mirror, bouncing sunlight back into space for years. The planet's thermostat was turned down drastically, and suddenly, we see the ghost of this winter in ice. Deep in the ice cores from Greenland and Antarctica, there's a sharp spike in sulfate, a chemical scream frozen in time, dated right to the era of Toba. The climate models from this evidence suggest global temperatures may have dropped 5 to 10 degrees Celsius. For a decade, summers vanished, growing seasons failed. For any species that needed a stable climate, including our ancestors, it was an existential crisis. This leads to one of the most intense debates, the Toba catastrophe theory. Some geneticists looking at human DNA have proposed that around this same time, our species went through a severe bottleneck. The genetic variation in all humans today suggests our ancestral population may have shrunk to just a few thousand breeding pairs. Could Toba have been the cause? Did this volcanic winter push Homo sapiens to the brink of extinction? The archaeological record tests this idea. There's one site in southern India called Jurassic. It offers a snapshot. Archaeologists found layers of soil with sophisticated stone tools, blades and scrapers made by modern humans, and right in the middle of this occupation layer is a thin, white line. The Toba ash fall. The tools are found below it and, crucially, immediately above it. This isn't a story of absence, it's a story of continuity. It suggests that here, at least, a group of people weathered that decade of darkness. They saw the sky dim, they felt the cold descend, they adapted, they persisted, and when the ash settled, they continued. The magnitude of Toba is hard to grasp. Compared to historic eruptions we know, the famous eruption of Krakatoa in 1883 was monumental. It darkened skies globally, lowered temperatures for a year. Toba is estimated to have been over 100 times more powerful, a different category of event entirely, a force that wrote its name not just in local geology, but in the genetic and cultural memory of humanity. So this thin, global layer of ash and sulfate, it tells us the Earth's story isn't one of gradual, peaceful change. Crisp, global signatures are stamped into the archives of ice and mud by sudden, violent paroxysms. The Toba super-eruption was a geological instant, but its winter lasted for generations. It asks a question about our place in this story. When the sky turns to dust and the cold lingers for years, what does a species do? The tools above the ash at Jurassic whisper one answer: we endure, we find a way through the long winter, and in doing that, we carry the memory forward. Not just in our genes, but in the very fact that we are here to uncover its layer in the Earth. The Mediterranean Sea dried up. It became a desert 2 miles deep. That's the Meishan salinity crisis. The evidence is right there in the seafloor. You drill down and you go through normal ocean mud, then your drill hits something else. For a kilometer, solid salt, thick layers of gypsum and halite, evaporites, they only form when a body of water is cut off and evaporates completely. The Mediterranean was blocked at Gibraltar. It turned into a giant salt pan, a lake sea, the Lago Mare. Its shores were canyons, rivers like the Nile, and the Rhone fell down into a basin far below where the sea is now. Then the flood happened. The Atlantic broke through at Gibraltar, a cataclysm of water. Today, the seafloor shows huge, scoured channels on both sides of the strait. Scars from a waterfall, the Atlantic was 5,000 feet higher. Water roared into the empty basin, a cascade hundreds of times bigger than Niagara. It filled the entire Mediterranean, an area larger than India, in maybe just a few years. The proof is in the rock above the salt. The chaotic evaporites are suddenly capped by a layer of fine, gray sediment. Open ocean mud, brought in by the new sea, the fossils switch instantly, from brackish water snail shells in the Lago Mare to plankton skeletons that need clear, normal ocean water. The Mediterranean was reborn in a geological instant. Its floor is a 2-mile thick book of stone with a single page turned between one world and the next. This power of water to reshape things isn't just ancient history. At the end of the last ice age, something similar happened in North America. A huge glacial lake, Lake Agassiz, covered central Canada. It was held back by a wall of ice. When that ice dam failed, it released a vast flood of freshwater into the Atlantic. This wasn't just local. You can see its signature in Greenland ice cores. There's a layer where the ice chemistry changes abruptly. It shows a sudden, major influx of freshwater onto the ocean surface. Freshwater is lighter than salt water. It can sit on top of the sea like a lid, and that's what this flood did. It's believed to have capped the North Atlantic, shutting down a crucial ocean current. The one that brings warm water north from the tropics. The result, recorded in ice and in lake sediments across Europe, was a rapid return to icy conditions. A period called the Younger Dryas. For over 1,000 years, just as the world was warming, it snapped back into cold, all from one pulse of water, disrupting the planet's circulation. These stories are held in the ledger of the rocks. A stratigrapher reading a core sample is an accountant of deep time. They see the deposits of a quiet sea, then the chaotic salts of a dried-up basin, then the orderly muds of a refilled ocean. Each layer is an entry, a balance sheet of evaporation and flood, of isolation and connection. It shows a planet where the line between land and sea isn't permanent. It's a temporary arrangement, waiting for the next shift in the tectonic plates or the next failure of an ice dam. The Mediterranean's salt and Lake Agassiz's flood ask us to see the Earth's surface for what it is. A dynamic, ever-changing canvas where water is the brush and the rocks are the final painting. Golden dust built a continent, a huge plateau in northern China, all soft yellow cliffs and hills. That's the lowest plateau. It wasn't made by water, it was made by wind. It's a monument of dust. For 2.5 million years, Ice Age winds picked up fine silt. From dried riverbeds in Central Asia, from glacial plains, they carried it east and they dropped it layer after layer until it was over 1,000 feet deep. That material is loess, and in that blanket of dust, scientists found a record. A detailed record of the planet's heartbeat, the pulse of the ice ages. To read it, you don't just look at the color, you read its physical story, its magnetic story. They take core samples from the cliffs. They measure the magnetic susceptibility of each layer. It sounds technical, but the idea is simple. During warm, wet periods, the interglacials, the dust slowed down, plants grew, a soil formed on the surface. A dark soil called a paleosol, richer in organic matter, richer in magnetic minerals. It shows up as a dark band in the golden cliff. Then the climate would shift back. Glaciers advanced, the land dried, the winds came back strong. Dust storms returned. They buried that old soil under new silt, light-colored and pristine. So you get this rhythm, a sequence of dark paleosols and light loess like pages in a book. Each pair is one full cycle, cold glacial, warm interglacial. The resolution is incredible. At Luochuan, you can stand before the cliff and see over 250 feet of this. You can trace dozens of cycles with your eye. But scientists go deeper. They analyze the grain size in each lowest layer. Thicker grains mean stronger winds, finer grains mean a less arid phase. They even look at snail shells. Tiny land snails trapped in the dust. Different species liked different climates, dry or humid, cold or warm. Their shells are little climate sensors preserved. This record on land doesn't stand alone. It matches the deep sea cores. The oxygen isotopes in plankton shells on the ocean floor tell the same global story. Ice volume, temperature. When you put the Chinese lowest next to the marine record, the patterns match almost perfectly. A dark soil layer in China lines up with a warm peak in the ocean. A thick, coarse lowest layer lines up with a glacial maximum. It's a convergence. It means the winds that built this plateau were synchronized with the ice sheets. Thousands of miles away, the dust was a global signal. This archive also has traces of our own story. As the climate cycled, the environments across Eurasia shifted. During dry, dusty glacial phases, the steppes expanded. That created corridors. During warmer, wetter interglacials, forests grew that could create barriers. The layers of loess and the stone tools sometimes found in them chart the possible migrations. Early humans moving with these shifting zones. The dust didn't just record the climate. It set the stage for the journey. It leaves you with a thought. We walk on landscapes we think are permanent, solid ground, but the lowest plateau shows the Earth can be a sky-born gift. An accumulation of ancient storms. What we see as rock and soil is a frozen weather report, a testament written in dust, patiently layered, waiting for us to learn its language. The rock record remembers fire, ancient fire, not in lava flows but in something smaller, microscopic charcoal, soot washed into ancient lakes and locked inside coal. To find it, scientists pull cores from lake beds, long tubes of mud. They wash that mud through sieves. What's left are tiny black fragments, angular. They count them under a microscope. Each one is a fleck of a forgotten blaze, a fossil spark. By tallying them down through the layers, they build a timeline. A chronicle of ancient flames. One chapter stands out, the Cretaceous, the dinosaur world. It's thought to have been a high fire world. The air was different then. Models suggest oxygen levels were higher, maybe 30% compared to 21 today. In that richer oxygen, fires would ignite easier, burn hotter. Spread faster through the forests. The evidence is in the rock, a material called fusane. It's a shiny black part of coal. Under the scope, it shows plant cell structure preserved as charcoal. That structure only survives if the plant was charred fast in a fire. So much of the coal from those ancient swamps contains the ghosts of fires that burned those same swamps before they were buried. The plants that became our fossil fuels were often fuel for ancient megafires. These charcoal layers are climate barometers. Scientists see spikes in charcoal at times of climate stress. The Paleocene-Eocene thermal maximum, that sudden global fever. In cores from that time, charcoal counts skyrocket. The world was warmer, drier in many places. Droughts were more severe, forests became tinder. A single lightning strike could leave a soot signature across a continent. The same pattern appears after the asteroid impact. In the famous boundary clay with the iridium and shocked quartz, there's a global layer of soot. The leading theory is the impact ignited worldwide firestorms. Superheated debris raining back through the atmosphere. The planet's forests may have burned in a single planet-encircling blaze. The charcoal in that clay is its ashen residue. For the long-term view, there's a lake like Frocker's Lake in British Columbia. Its sediments hold over 10,000 years of fire history. Scientists pull a core and count the charcoal peaks, layer by layer. Then they match those peaks to other records, tree rings that show drought. The correlation is striking. The biggest charcoal layers line up with the driest centuries. It reveals a cycle. Climate determines the fuel. A warm, dry phase builds up flammable vegetation. Then a spark, lightning, a volcano, a meteorite transforms that fuel into a firestorm, which leaves its microscopic signature in the mud at the bottom of a quiet lake. That mud hardens into stone, preserving the memory. This asks us to reconsider something ephemeral. A wildfire seems transient. It roars through and is gone. But paleofire science shows fire is a permanent sculptor. Its chemical fingerprint survives for hundreds of millions of years. It writes itself into the geological ledger as surely as an ocean or a glacier. The relationship is a triad: climate, vegetation, and fire. Change one, and you change the potential of the others. The charcoal fragments are a reminder. Our planet's story isn't just growth and accumulation. It's also periodic cleansing consumption. The Earth has always known how to burn. And the stones have never forgotten a single spark. The rocks hold another kind of poison, a burning rain. The evidence isn't in the ash, it's in the weight of sulfur atoms. At the boundary of the Great Dying, the isotopes of sulfur go wild. They're trapped in minerals like pyrite, and they fluctuate. That only happens when the atmosphere loses its ability to process sulfur normally. It's a chemical scream. It points to a sky flooded with sulfur dioxide from volcanoes. To see this, you need incredible precision, mass spectrometers. They can weigh atoms. They distinguish the heavier sulfur-34 from the lighter sulfur-32. In a normal world, biological and geological processes handle these isotopes in predictable ways. But during the End-Permian, that predictability shattered. The signal is a colossal overload. The Siberian Traps weren't just pouring lava. They were belching billions of tons of sulfur dioxide into the stratosphere. There, it mixed with water vapor and sunlight. It became sulfuric acid aerosols, tiny droplets. They fell globally as corrosive rain. This acid rain did two things. It scorched the land, it leached nutrients from soils and damaged plants, and it poured into the oceans. It lowered their pH in a wave of acidification. That came before the suffocation. The sulfur isotopes in marine rocks capture the exact moment this toxic rain began to change the chemistry of the sea. There's a similar signal in more recent archives, much smaller. Lake sediments and glacial ice from the 20th century have a clear layer, a spike in sulfate. A shift in acidity. It's directly linked to burning coal. The human-made acid rain crisis of the mid-1900s is already written into the planet's newest geological layers. It's a faint echo of the Permian, a proof of concept. Our actions can write the same kind of chemical signature into stone. One researcher noted the difference is scale and speed. The Siberian Traps emitted over hundreds of thousands of years. We've done something comparable in decades. That forces a question. When future geochemists, a million years from now, drill into the thin layer of our epoch, what will the sulfur isotopes tell them? Will they see a brief, sharp spike of atmospheric poison, then a return to balance? Or will they see the beginning of a longer, more permanent shift? The language of isotopes is quiet, but its message is deafening. The sky has a memory. And the stones below are patiently taking notes. Beneath the ocean floor, there's a frozen dragon. It's not a creature, it's a structure, a lattice of water ice that forms a cage, trapping molecules of methane gas inside. These are methane clathrates. They exist in a delicate balance. They're stable only under the immense pressure of deep water and the cold of the seabed. You disturb that balance and the cage melts, the dragon wakes, and its breath is a potent greenhouse gas. This is the heart of the methane gun hypothesis. It suggests that past episodes of abrupt warming, they might have been triggered by the destabilization of these vast, frozen carbon reservoirs. The gun wasn't fired by a volcano or an asteroid. It was fired by the planet's own warming, unlocking a buried feedback loop. How do we know this happened? The evidence is written in atomic weights. Carbon atoms come in two stable isotopes. Carbon-12, which is light, and carbon-13, which is slightly heavier. Living things like the microbes that produce methane, they strongly prefer the lighter carbon-12. So methane from clathrates is exceptionally light. When that methane is released and it oxidizes to carbon dioxide, and enters the ocean and atmosphere, it floods the global carbon cycle with this light signature. Organisms that build shells or plants that grow, they incorporate that light carbon. The result is a sudden, sharp negative swing in the carbon isotope ratio. It's preserved in limestone and organic matter. It's a geochemical fingerprint, a smoking gun left at the scene. This signature is clearest during hypothermal events, those rapid global warming spikes. The Paleocene-Eocene thermal maximum, the PETM, it shows one of the most dramatic excursions ever recorded. In ocean sediment cores, the isotope curve doesn't just dip. It plunges. This tells scientists the carbon came from a reservoir that had been isolated from the atmosphere for a very long time. A reservoir rich in biological carbon. Methane hydrates fit that profile perfectly, but what pulls the trigger? Several mechanisms can disturb the stability zone. A drop in sea level, like during the onset of an ice age, reduces the pressure on the seafloor. That can melt shallow hydrates. Underwater landslides triggered by earthquakes or sediment collapse can expose hydrates to warmer water almost instantly. Or a gradual warming of deep ocean currents over centuries can slowly eat away at the base of the stability zone, causing chronic, widespread leakage. To study these deposits today, scientists go to places like the Blake Ridge off the coast of the Carolinas. Seismic surveys there reveal vast fields of clathrates buried in the sediment. Drill cores bring up chunks of sediment that fizz as the pressure is released. The ice melts and the methane escapes. These modern studies help calibrate the models. They show just how much carbon is stored in this fragile, icy form. So, revisiting the PETM, the debate isn't whether there was a massive release of light carbon. The isotope record is unequivocal. The debate is about the source. Was it a direct blast from clathrates, a first strike that set off the warming, or was it a secondary feedback? An initial warming from volcanic carbon dioxide warmed the oceans just enough to start melting hydrates, which released methane, which caused more warming. In a vicious, amplifying cycle, many researchers now lean toward this latter view. The methane gun wasn't the lone assassin, it was a crucial accomplice. One that turned a warming event into a planet-wide fever. This forces a reflection on fragility. For millions of years, these icy compounds have acted as a planetary carbon capacitor, storing greenhouse gases away from the atmosphere, but the rocks tell us this capacitor can discharge rapidly, and when it does, the isotopic signal it leaves is a stark warning etched into the geological record. It shows the planet's climate system has tripwires buried in its own seabed, lines that, once crossed, can unleash forces that rewrite the world for millennia. That thin, dark line in the ice, the Younger Dryas, there's a new suspect for it, under a strange layer of sediment, a black mat found in places across North America. Researchers found something microscopic, nanodiamonds, tiny, a few billionths of a meter across. They form under immense heat and pressure. They were found with other particles, magnetic spherules, tiny grains of high-temperature minerals. For a team of scientists like geophysicist Alan West and archaeologist James Kennett, these weren't random, they were shrapnel, scattered shrapnel from a cosmic catastrophe. Their idea is that 12,800 years ago, as the last ice age was ending, a comet or asteroid broke apart. It exploded in the atmosphere over the North American ice sheet. The proposed sequence is a cascade. First, the airburst or impacts raining fire across the continent. The evidence for that is in the black mat itself. That layer is often full of charcoal and soot, which suggests continent-wide wildfires. The intense heat would have melted huge portions of the Laurentide ice sheet. That sudden meltwater pulse, they argue, flowed into the Atlantic or the Arctic, capping the ocean's surface with freshwater. That lid would have shut down the Atlantic meridional overturning circulation. The current that brings warm water north, the result was the Younger Dryas, a sudden 1,200-year return to glacial cold, exactly as the Greenland ice records it. This theory connects dots across fields astronomy, geology, climatology, archaeology. It offers one dramatic explanation for several things that happened around the same time. The extinction of North America's megafauna, mammoths, mastodons, the disappearance of the Clovis culture, and that abrupt climate reversal. But from the start, this idea has faced intense scrutiny. The geological community is divided. Proponents point to other evidence, a distinct platinum spike in Greenland ice cores from that exact time. Platinum is rare in Earth's crust but common in space objects. They also cite sites with what they think is shocked quartz, a classic impact indicator. Skeptics counter that many of these markers aren't unique to impacts. Nanodiamonds can form in extreme wildfires. The magnetic spherules could be from terrestrial processes. They say the evidence is patchy. that the black mat is better explained by wetland development in a changing climate. The debate often comes down to reproducibility. Some labs find the exotic materials, others at the same sites do not. One of the most compelling pieces of this puzzle comes from a site far from the ice. Abu Huraira in modern-day Syria. It was a settlement of hunter-gatherers right at this moment. In the layer dating to 12,800 years ago, researchers found evidence of intense burning. They found tiny spheres of siliceous scoria, a melted, glassy material, and nanodiamonds in the building material. The team there suggests this is evidence of the airburst effects reaching across the globe. And the archaeological record shows something else. Right after this layer, the people of Abu Huraira transitioned from hunting gazelle to cultivating grains like rye. Could a global climate shock from a cosmic impact have been the catalyst for the dawn of agriculture in the Fertile Crescent? It's a profound connection. A speculative one. A leading skeptic, geologist David Meltzer, argues the hypothesis tries to explain too much with one cause. He notes the megafaunal extinctions were staggered over time. That human hunting played a big role. He questions whether the climatic changes were truly as abrupt as the impact theory requires, suggesting the transition into the younger dryas may have been more complex. This conversation is the sound of science at work, a rigorous, often contentious process, claim and counterclaim. So how is consensus built from fragmented, controversial evidence? It's not built on a single discovery. It's built on a convergence of lines of inquiry, independently verified, repeatedly tested. It requires the evidence be found in the right sequence, in the right context by multiple teams. The KPG boundary layer succeeded because its signals were global, unmistakable, and ultimately linked to a crater. The younger dryas boundary hypothesis is still in the courtroom. The jury is out, but this detective work in Earth's most recent layers is revealing. It shows a scientific frontier where the rocks are still being read. And the story of our planet's sudden changes is still being written. Under the Mediterranean, there's a graveyard of salt. Seismic profiles show it like sonograms of the Earth. Beneath younger muds, there's a layer. In places, it's over 2 kilometers thick, and it's not orderly sediment. It's a chaotic, jumbled mass, salt and gypsum. Geologists call it the Messinian Evaporite sequence, one of the planet's great saline giants, but it's not a single event. It's a story told in repeating, desperate cycles. The layers aren't flat, they're deformed, folded and broken. That chaos tells you the Mediterranean didn't just dry up once, it did it over and over. The mechanics were a slow-motion tectonic drama. The African plate pushing north into Europe. That collision slowly pinched shut the gateway at Gibraltar. It raised a sill, a shallow underwater ridge. Eventually, the connection to the Atlantic was severed. The Mediterranean became a giant bathtub with the plug pulled out. Its only input was rivers, and that wasn't nearly enough to balance the evaporation under the hot sun. The sea level inside the basin began to drop, hundreds of feet, then thousands. Shorelines retreated down canyon walls that are now submerged. What was left was a hellscape of concentrated brine. The evaporite minerals themselves are a chemical diary. The first to form as the water concentrates is gypsum. Those translucent crystals, they precipitate out in shallow, warm lagoons. As more water vanishes, the brine gets so salty that halite crystallizes common table salt. In the deepest, most desperate basins, even more exotic salts would form, like sylvite, a source of potash. Each mineral is a marker on a gauge of desiccation. The sequence in the rocks, gypsum layers giving way to massive beds of halite, charts the descent from a dying sea to a barren salt pan. In Sicily, you can walk through this history. The mountains there are made of it. At the Relmont salt mine, you descend into a cathedral of white. The walls are pure halite, striped with layers of darker clay. Each stripe is a climate cycle. A dark layer might be a brief, wetter period, when a river managed to reach the basin depositing silt. Then a thick band of pure salt tells of a long, parched phase, where nothing but evaporation happened. This cyclicity is the key. It suggests the gateway at Gibraltar wasn't just closed and then blown open. It was a wobbly valve. Tectonic adjustments or small changes in global sea level would allow a trickle of Atlantic water back in, creating a short-lived brackish lake. Then the connection would seal again and evaporation would resume. This happened perhaps dozens of times over 600,000 years. The life that endured this was microscopic and tough. In the hypersaline lakes, only certain extremophile bacteria and archaea could thrive. They left behind distinctive organic compounds and strange, layered structures called microbial mats. Then, in the sediments that immediately cap the salt, the fossil record explodes. The tiny, delicate shells of open ocean plankton suddenly reappear. That's the biological signal of the Zanclean flood. The Atlantic finally won catastrophically. The implications stretched far beyond the basin. Oceanographers model what happens when you remove a sea. The Mediterranean holds about 1/10 of the world's ocean salt. Locking that away in a desert basin dramatically lowered the salinity of the rest of the world's oceans. That changed their density and therefore their global circulation patterns. The climate of Europe and North Africa was fundamentally different during this time, dominated by the vast, low-lying desert where one of the world's great seas had been. Today, we mine these layers for the salt on our tables and the potash that fertilizes our crops. We're harvesting the mineral remains of an ancient climate disaster. It asks a question about scale. A local tectonic event, the closing of a strait, didn't just create a regional oddity. It altered the chemistry of the global ocean and reshaped climates on a continental scale. The planet's systems are linked in a silent, powerful conversation, and the Mediterranean salt is a shout that was frozen in stone. You cut into this ancient lake mud and you see a rhythm, these perfect thin stripes, a light band, then a dark one, then another light, another dark. They're called varves. It's nature's most precise calendar written in mud. In a quiet lake, the seasons leave their mark every single year. In the summer, meltwater and rain wash in fine silt and clay. These particles are light in color. They drift down slowly and they settle into a pale layer. Then winter comes, the lake surface freezes over, the inflow of silt just stops. And in that cold, dark water under the ice, microscopic algae die. Their remains, along with other organic debris, they slowly rain down. That material is dark. It forms a thin, black layer right on top of the summer's silt. One light and one dark pair, that's 1 year. A single page in a climate diary. The clarity of this record is breathtaking. At Lake Suijutsu in Japan, scientists pulled a core that has over 70,000 of these annual layers. That's an unbroken timeline, stretching all the way back to the last ice age. You can hold a section of that core and count the years one by one, like reading rings on a tree. But varves are more than a calendar. They're a multi-proxy archive. Inside each tiny dark layer, scientists find fossil pollen grains, and those tell you what trees and plants grew in the watershed that year. A spike in pine pollen suggests a cool, dry phase. An increase in oak pollen points to a warmer, wetter period. They also analyze the chemistry of the layers. The ratio of different oxygen isotopes in the sediment can reveal the temperature of the water when that layer formed. Thicker layers of summer silt often mean a year of heavy glacial melt or intense rainfall. Thinner pairs might indicate drought. This precision allows for incredible correlations. Varves from lakes in Europe have been used to date archaeological sites precisely. A settlement layer found between specific varves in a Swiss lake can be pinned to an exact year, sometimes even a specific season. More powerfully, VARVs let scientists synchronize climate events across the globe. A volcanic ash layer from a known eruption found within a VARV sequence in Germany can be matched to an ice core layer in Greenland. This creates a unified timeline. It stitches together the story of the Northern Hemisphere's climate. The same process happens in the sea under the right conditions. In the Santa Barbara Basin off California, the seafloor is anoxic, devoid of oxygen. That lack of oxygen means no burrowing worms or other creatures live there to churn up the sediment. So the annual layers stay perfectly preserved. Here, the VARVs tell a different story. The dark layers are rich in organic matter from plankton blooms. The light layers are mostly clay. The thickness of these dark layers is a direct record of ocean productivity, and within this sequence, scientists see a familiar pattern. Clusters of thin VARVs indicating poor productivity. They line up perfectly with historical records of strong El Niño events. The ocean's rhythm, driven by Pacific climate cycles, is captured in this submerged mud. Maybe one of the most elegant examples is Lake Kasjön in Sweden. Its VARVed sediments have built up for over 8,000 years. By measuring the thickness of each summer layer, researchers have reconstructed a high-resolution history of Scandinavian climate. They can see not just the broad sweep of the warm medieval period or the Little Ice Age, but the subtle, year-to-year fluctuations within them. A series of thin VARVs in the 1400s might indicate a cluster of cold, harsh summers. Summers that impacted harvests and societies in ways the broader historical record has missed. This is climate history written in the most intimate detail possible. It makes you pause at the quiet efficiency of it all. Without any human observer, without any instrument, the Earth has been keeping a meticulous logbook. In the still waters of a lake or a secluded basin, season after season, it laid down this rhythmic testimony. Each VARV is a sentence, each core is a volume. And in that library of mud, we find a truth more precise than we could have ever invented. The planet remembers in stunning detail exactly what happened. One perfect stripe at a time. There's this huge fossil coral head. It was pulled up from an ancient seabed, and it has rings like a stone tree. Each band is a season, a year, a decade of ocean memory. That's sclerochronology, the study of hard biological tissues. It gives us a diary of the seas written in living stone. Corals are meticulous recorders. As they grow, they pull calcium carbonate from the water to build their skeletons, and inside that mineral lattice, they trap a chemical snapshot of the ocean they lived in. To read it, scientists use a delicate drill, thinner than a human hair. They extract microscopic samples along a single growth band, moving from the coral's youth to its final days. The most telling signature is written in oxygen atoms. Oxygen comes in two stable isotopes, oxygen-16, which is lighter, and oxygen-18, which is slightly heavier. When water evaporates from the ocean surface, the lighter oxygen-16 evaporates more easily. So during an ice age, when lots of light oxygen is locked up in glaciers, the seawater left behind gets enriched in heavy oxygen-18. Corals incorporate that heavier signal into their skeletons, but temperature also plays a role. In warmer water, corals are less discriminatory. They use a bit more of the heavy oxygen-18. By untangling these two effects, often with help from other elements, geochemists can use the oxygen ratio as both a thermometer and a rough gauge of past salinity. They also analyze trace elements like strontium and magnesium. The ratio of strontium to calcium in a coral skeleton decreases as the water temperature rises. That gives another independent check on the ancient climate. Some of the most crucial readings come from fossil reefs of the Pliocene epoch, about 3 million years ago. This period is a key focus because carbon dioxide levels in the atmosphere were similar to what we have today. and global temperatures were about 2 to 3 degrees Celsius warmer. Corals from this time, found in places like the Caribbean and the Pacific, show us what a stabilized warm world looks like. They indicate sea levels were substantially higher. Perhaps by up to 20 meters, the warmer oceans had expanded and ice sheets on Greenland and Antarctica were smaller. These fossil reefs are not just relics. They are direct analogues. They show the long-term equilibrium state of a climate system with our current CO2 concentration. On the island of Papua New Guinea, there are spectacular terraces of uplifted fossil reefs. They stair-step their way up the mountainsides. This dramatic landscape is the result of tectonic forces pushing the seafloor upward. But locked within each terrace is a record of when that reef was alive and growing at sea level. By dating these coral platforms, scientists can reconstruct not just past ocean temperatures, but the precise history of sea level change and the rapid tectonic uplift of the land itself. It's a double archive of both climate and the restless Earth. Perhaps one of the most detailed records doesn't come from a coral, but from another form of calcium carbonate. In Nevada's Devil's Hole, a fissure in the rock filled with water, thin veins of calcite have precipitated on the walls for hundreds of thousands of years. These layers, much like coral bands, preserve a super high-resolution record of groundwater chemistry, which in turn reflects past rainfall and climate patterns in the region over 500,000 years. It's another example of how the planet inscribes its history in stone in the most unexpected places. A telling case study comes from corals that grew during the last interglacial period. About 125,000 years ago, this was a naturally warm phase between ice ages, with sea levels several meters higher than today. Detailed analysis of these fossil corals reveals something subtle but significant. The pattern of the geochemical bands suggests that the tropical Pacific Ocean experienced more frequent swings in temperature. Similar to modern El Niño events, this implies that in a warmer world, the engine of tropical climate may operate differently, with potential ripple effects across the globe. It's a profound realization. A living organism filtering the sea becomes a library. Its skeleton, meant for support, becomes a ledger of light, temperature, and chemistry. These biological archives add a vital layer to the story told by sediments and ice. They provide the seasonal resolution, the fine print that other records often lack. They remind us that the climate is not an abstract force, but the very water in which life breathes and builds. And in its enduring stone, that life tells us exactly what that water was like. Deep underground, in that quiet where you only hear water dripping, the Earth is keeping a different kind of record. In caves all over, you have these stalagmites coming up from the floor. Like stone candles, and each layer is a moment of ancient rain, frozen. They're more than just rock formations. They're some of the most precise rain gauges we have. They track the monsoon's pulse, the long stretches of drought, across hundreds of thousands of years. In China, in Hulu Cave, scientists have pulled out speleothems that grew through the entire last ice age cycle. If you hold a cross-section, you're holding a timeline, a core of creamy calcite with these bands, subtle shifts in color and texture. Each ring is a page. A climate diary kept underground. It starts with one drop, rainwater falls, then it seeps down, through soil, through bedrock, and as it travels, it picks up a little carbon dioxide from the air and the soil. That makes it a weak acid, so then it dissolves tiny bits of calcite from the limestone above the cave. By the time the water drips from the cave ceiling, it's full of dissolved calcium carbonate. When a drop hangs and falls, it releases some carbon dioxide into the cave air. That changes the water's chemistry, just enough. It forces a tiny, almost invisible amount of calcite to come out of the water. That microscopic deposit, that's the start of a stalagmite. Then, over centuries, drip by drip, layer on layer, it grows upward, and it records the chemistry of every single drop. The key is what the water carries with it. That percolating rainwater picks up two signatures from the world above. First, the oxygen isotopes in the water itself. The ratio of heavy oxygen 18 to light oxygen 16. That ratio changes with temperature, with how far the rain traveled, with the strength of a monsoon. So a layer from a strong, warm monsoon has a different oxygen isotope ratio than one from a dry, cool time. Second, the water picks up trace elements from the soil and rock. Things like magnesium and strontium. Their concentrations tell you how much water was moving through the system, which is a proxy for how hard it was raining above the cave. To read this diary, you need the date for each entry. That's where Uranium-Thorium dating comes in. As the calcite layer forms, it traps tiny amounts of uranium from the groundwater. Uranium is radioactive. It decays into thorium at a known constant rate, and thorium doesn't dissolve in water, so it gets locked into the calcite the moment that layer forms. So scientists take a microscopic sample from a specific growth band. They measure the ratio of uranium to thorium, and from that they can calculate its age. With incredible precision, often within a few decades for a layer that's tens of thousands of years old. That turns the speleothem from a pretty rock into a calibrated climate instrument. The stories these stone pillars tell are global. A stalagmite from Borneo, for instance, gives a 100,000-year record of El Niño. During strong El Niño years, the Western Pacific often gets drought. The stalagmite's growth slows, its oxygen isotope ratio shifts. By matching this ancient record to modern data, researchers have extended our view of this climate cycle deep into the past. Showing its natural rhythms, maybe the most human connection comes from the Yucatán Peninsula, the heart of the ancient Maya world. Stalagmites there show a clear pattern. Severe drought in the 9th century, lasting decades. The growth layers get thin. The geochemical signals all point to water stress, and this period of intense dryness lines up exactly with the archaeological evidence for the classic Maya collapse. A time of societal upheaval, agricultural failure, cities abandoned. The cave stone doesn't record the human suffering, but it records the environmental pressure that shaped it. It links a civilization's fate directly to the fickle rains they depended on. It makes you think, beneath our feet, in the cool dark of countless caves, these silent stone sentinels are still growing. They are recording our present climate, drip by patient drip. What will their layers forming right now tell future scientists about the rainfall of our era? In their intricate bands, they hold the memory of past climates and a quiet, ongoing testimony of the world above, a hidden history of the sky, written in stone deep within the earth. Beneath the ground, there's a whole other world, not rock, not sediment, ancient dirt, a fossilized landscape, a paleosol. These aren't just layers, they're portraits of lost climates. Captured by luck when a flood or a windstorm buried them suddenly, sealing the story away. You might see one in a cliff face, a bright band, a deep, rusty red. That red is the ghost of iron, oxidized in a warm, wet, oxygen-rich atmosphere. It's a chemical photograph, an ancient summer, maybe millions of years old. Scientists who study this are detectives of buried ground, paleopathologists. They don't just see dirt, they see a system. They look at fossilized root traces. The shape and chemistry, delicate, branching traces mean grasses, thick, vertical ones point to trees. They study hard lumps called nodules. If they're calcium carbonate, that's a clue from aridity. In dry climates, water evaporates upward. It draws dissolved calcium to the surface, where it cements into a hardpan, caliche. The depth of these nodules is a rain gauge. Deep caliche means occasional heavy rains. Shallow, dense caliche means persistent drought. The minerals themselves are a climate report. A paleosol rich in a clay called kaolinite tells of a different world. Kaolinite forms under relentless tropical rainfall. Rain that leaches nearly everything else away, leaving this stable, weathered clay. It's the signature of a hot, soaked planet. Walk through the Badlands of South Dakota. You're walking across an album of these fossilized landscapes. The striated cliffs aren't just sand and mud. They're sequences of ancient soils stacked one on another. At the base, you might find a thick, dark paleosol with deep root casts of trees. This was a forested floodplain. Humid and lush, then your eye travels up the cliff. The soils change. They become thinner, lighter in color. Those carbonate nodules appear closer to the surface. The root traces shift to finer patterns of grasses. The story in the stone is clear. A slow, multi-million-year transition from a wet, wooded world to a drier, open grassland. The ground itself evolved. Some of the most transformative paleosols are far older, from the Carboniferous period, the soils that supported the first great forests. They are often packed with fossilized root masses, a distinctive speckled organic layer. Their formation was a planetary event. Those pioneering trees with deep roots broke rock down into soil at an unprecedented rate. That chemical weathering pulled vast amounts of carbon dioxide from the atmosphere, locking it away in carbonate minerals and organic matter. The paleosols are the tangible record of this drawdown. A major factor in the global cooling that followed, we can see a much faster change recorded in paleosols at the Paleocene-Eocene boundary, in places like Wyoming. The fossil soils show a dramatic, sudden shift. The layers become intensely weathered, stained with iron oxides, leached of soluble minerals. This is the mark of a climate shock. The rapid warming and increased rainfall of the PETM, it turbocharged the weathering engine. The ground itself was reacting chemically to the fevered atmosphere above it, trying to pull the excess carbon back down. So the next time you stand on solid ground, consider this. The soil isn't just dirt, it's a living, breathing skin. It interacts with the air and the climate, and when it's fossilized, it becomes a sealed diary. It remembers the rainfall that fed its plants, the warmth that baked its surface. The very composition of the ancient air. These profound climate secrets aren't always in deep oceans or icy cores. Sometimes they're waiting in the ancient dirt. In the quiet, colorful bands of a crumbling cliff, offering a grounded truth about a world long gone. That ancient dirt tells one story, but the polar ice holds another. It's a frozen library. It preserves the actual air of the past. In Greenland and Antarctica, scientists drill deep. They pull up cylinders of ice. These are time capsules of the atmosphere. The cores contain layers of compressed snow. Some of that snow fell 800,000 years ago, and trapped in that ice are tiny bubbles, bubbles of ancient air. Samples of the planet's atmosphere from a specific moment in deep time. This gives us something the rock record can't, a direct measurement. Researchers crack these bubbles open in a vacuum. They analyze the exact concentration of carbon dioxide and methane, the exact concentration from when that snow fell. They can trace the rise and fall of these greenhouse gases across hundreds of millennia. Alongside the gas, the ice itself is a chemical thermometer. The ratio of heavy to light oxygen isotopes in the frozen water. That ratio is a reliable proxy for the temperature when the snow formed. A higher proportion of the heavy isotope generally means a warmer climate. So from one core you get a synchronized record, temperature and atmospheric composition. Year by year, millennium by millennium, the iconic records come from places like Vostok Station in Antarctica or the Epica site. The Epica core traces 8 full glacial cycles. The graph it produces is stunning. It shows a sawtooth pattern, a long, slow descent into an ice age, then a relatively rapid warming into an interglacial period. Like our own, and superimposed perfectly on that temperature curve is the carbon dioxide curve. When temperatures are low, CO2 is low. When temperatures rise, CO2 rises. The coupling is undeniable, precise. It's the most direct evidence we have, evidence that greenhouse gases and climate are linked across Earth's history. Beyond gases and isotopes, the ice is a ledger of events. A dark layer might be volcanic ash or dust from a distant desert storm, and here is a crucial bridge to the rock archives. Volcanic ash has a unique geochemical fingerprint. The specific ratios of elements in tiny glass shards, they act like a barcode. Scientists can take ash from a layer in an ice core, analyze its chemistry, then match it to an identical ash layer in a sedimentary rock sequence on another continent. This technique is called tephrochronology. It creates a pin in the timeline. It lets us say with certainty that this event in the Greenland ice is the same eruption that left its mark in a lake bed in Germany, or an ocean floor in the Pacific. It synchronizes the frozen and the stone records into one calendar. We see this powerful link with events we've already looked at. Take the Younger Dryas, that sudden cold snap 12,800 years ago. In the Greenland ice cores, it appears as a dramatic plunge in temperature isotopes. A layer of increased dust, a change in snowfall chemistry. This frozen signal of abrupt cooling can then be searched for in terrestrial records, in the valves of European lakes, or in the fossil pollen of North American bogs. The ice provides the precise timing, the global context for changes we see on the ground. Or consider the Toba super-eruption. Its signature is a massive spike of sulfate aerosols in both Greenland and Antarctic ice, dated to about 74,000 years ago. That same sulfate signal, carried by global winds, washed into the sea. It can be found as a chemical enhancement in marine sediment cores from the Indian Ocean, one cataclysm, recorded simultaneously in ice at the poles and in mud at the equator. It's a perfect triangulation of Earth's memory. This synthesis asks a question. What do we learn when we listen to all of Earth's archives together? The rocks give us the long view, the monumental shifts in oceans and continents. The ice gives us the fine details, the year-by-year chemistry of the air. The corals and caves add seasonal resolution. By weaving them together, we move from fragments to the story itself. We see not just isolated events, but a planet whose systems are in constant conversation. Its atmosphere, its oceans, its ice, its bedrock, the frozen cores and the stone layers are not competing histories. They are different chapters of the same autobiography, written in different inks, waiting for us to learn how to read them as one. The continents move slowly, and that movement is the planet's real climate control. For more than 200 million years, the surface has been rearranged. Since the supercontinent Pangaea broke apart, that breakup didn't just move land. It cracked the crust open, and that unleashed geological forces that wrote some of the most dramatic chapters in the climate record. The mechanism behind it is called a large igneous province. And it's not a normal volcano. It's a catastrophic release of molten rock from deep in the mantle, erupting through the continental crust in enormous floods. These aren't brief. They can last hundreds of thousands of years, covering areas the size of continents with layer after layer of lava, and they release staggering volumes of gas. The Siberian Traps linked to the Great Dying are a classic LIP. So is the Central Atlantic Magmatic Province. That's tied to the later Triassic-Jurassic extinction. These aren't coincidences. The breakup of Pangaea created the weaknesses, the cracks that let these mantle plumes reach the surface, so the volcanism was the trigger. But the tectonic setting set the stage. This deep Earth connection goes beyond volcanism. Think about a major mountain range rising, like the Himalayas. That uplift began when India collided with Asia. It's slow, but the climate impact is profound. As these new mountains are thrust up, they're exposed to wind and rain. The rock begins to weather. Chemical weathering is a powerful planetary thermostat. Silicate minerals in the mountains react with carbon dioxide in rainwater. They form new minerals, bicarbonate ions washed into the ocean. Eventually they form limestone on the seafloor, locking the carbon away, so the building of the Himalayas started a slow drawdown. A multi-million-year drawdown of atmospheric carbon dioxide that contributed to the global cooling trend, the cooling that led into our current ice age cycle. It's a fundamental feedback. Tectonics builds the mountains accelerate weathering, weathering cools the planet. Continental movement also controls the ocean's highways. About 3 million years ago, a final connection was made. The Isthmus of Panama rose from the sea, permanently separating the Atlantic and Pacific. This local event rerouted the whole planet's ocean circulation. Before the isthmus, warm equatorial waters could flow freely between the oceans. After it closed, that flow was blocked. Atlantic water was forced northward, along what we now call the Gulf Stream. This intensified current carried vast heat and moisture to the high latitudes of the North Atlantic. The increased precipitation there fell as snow, helping to build the massive ice sheets that have characterized the Northern Hemisphere ever since. The closure of a single seaway didn't just change a map, it helped plunge half the world into an ice age. Even the seafloor plays a role, the rate at which new oceanic crust is formed at mid-ocean ridges. That dictates how much volcanic carbon dioxide is released from Earth's interior. During periods of rapid seafloor spreading, more crust is created. More CO2 is vented from these underwater volcanoes. That can contribute to a warmer greenhouse world. When spreading slows, that input diminishes. Then weathering processes can reduce CO2 levels and cool the climate. It's a grand, slow-motion balancing act between the Earth's internal heat engine and its surface processes. There's a case study that brings this tectonic perspective to a moment we know. The end Cretaceous extinction, the Chicxulub impact. In the rock layers just below that asteroid dust in India lies another vast volcanic province. The Deccan Traps. This LIP was erupting violently in the several 100,000 years leading up to the impact. The gases from these eruptions, sulfur dioxide and carbon dioxide, would have already been stressing the global climate, causing short-term cooling from aerosols, then longer-term warming. Ecosystems may have been weakened, food chains strained, then the asteroid struck. Many paleontologists now see this as a one-two punch. The tectonic trigger of the Deccan Traps set the stage. By destabilizing the world's climate, the cosmic impact delivered the final, decisive blow. It shows how Earth's internal and external forces can converge to rewrite the story of life. When you step back to this tectonic canvas, a realization emerges. The climate disasters fossilized in the rocks, the extinctions, the ice ages, the dead zones, they are rarely random accidents. They are often the consequence of the planet's own deep internal rhythms. The opening and closing of ocean gateways, the colossal outpourings of lava from a restless mantle, the slow, grinding rise of mountains that scrub the air clean. Our planet's climate is not a passive system. It is actively, constantly shaped by the engine of plate tectonics. The rock record is the archive of that relationship. A testament, the ground beneath our feet, shifting at the pace of a growing fingernail, is the ultimate author of the world above. There was a horse, a tiny one. No bigger than a house cat, it lived in a world that was fevered. That's the Lilliput fossil, from the Paleocene-Eocene thermal maximum, and it's not a story about extinction. It's about stress, intense stress, because the planet was warming fast, and many mammal species, they shrank. They got a lot smaller. The cause was probably nutrition. A crisis there. In that high carbon dioxide air, plants grew faster, but they became less nutritious. so for an herbivore to survive, you needed less food. Evolution favored a smaller body. That dwarfing, it's a signal, a biological one, a whisper from an ecosystem under pressure, preserved in bone. Paleontologists, they've become detectives for that kind of stress. They read it in bone, in shell, in leaf. They look beyond just size, they look at shape, they look at chemistry. During an ocean acidification event like the one at the end of the Permian, the fossil record shows it. Plankton shells, they become malformed, a plague of them. For creatures that build shells from calcium carbonate, corrosive water is a direct assault. Their skeletons grow twisted or thin or pitted. It's a distress call, preserved in stone for hundreds of millions of years. To measure that, scientists now have tools. Boron isotope analysis. Boron's behavior in seawater is controlled by pH, tightly. When foraminifera, those single-celled plankton, build their shells, they incorporate boron. And they lock in a signature, a precise one, of the ocean's acidity right then. So researchers drill into these microscopic fossils from deep-sea cores. And they can reconstruct it, the pH history of the seas. It's like finding a stack of ancient litmus tests, each one a page from a logbook, an ocean chemistry logbook. The fossil record is full of these biotic barometers. The simple abundance of a species can be an indicator. In sediment cores, you see a layer dominated by plankton that prefer warm water. Then a sudden shift to plankton that prefer cool water that charts an ice age passing. Coral reefs tell a similar story. The robust branching corals, they thrive in clear, stable water. But during thermal stress or with murky runoff, they give way to slower growing massive corals, or they vanish entirely. Even disease in fossils, unusual lesions on shells or bones. That can spike during environmental turmoil, when immune systems are compromised. On land, fossil leaves are sensors, exquisite ones. Botanists have seen that when atmospheric CO2 is high, many plants reduce their pores. Their stomata, they don't need as many to take in the gas, and that relationship holds in the fossil record. So you count the stomatal density on a Cretaceous leaf. And you can make a strong estimate of the carbon dioxide levels in that ancient air. Another method is leaf margin analysis. It uses a simple fact. Plants in warmer climates often have smooth-edged leaves. In cooler areas, the leaves have jagged, toothed margins. So a fossil bed full of smooth-edged leaves paints a picture, a warm one, maybe tropical, but maybe the most detailed chronicle comes from those foraminifera. In the deep sea mud, across the thin layer that marks the PETM, their story unfolds, step by step. First, in the shells just below the boundary, the carbon isotope ratio plummets. That signals the massive carbon release. Then, in the shells within the boundary layer, the boron isotopes shift. That confirms the ocean turned more acidic. And finally, the shells themselves, they become smaller, thinner, less abundant. That shows the biological cost. So in a few centimeters of sediment, you have a dossier. A complete one on a global crisis. It forces a reflection, a profound one. Life is not just a passive victim of climate change. It's an active recording instrument. A sensitive one. Every organism from a tree to a plankton interacts with its environment, and that interaction leaves a signature, a chemical one, a physical one. So fossils are more than bones and shells. They are climate witnesses. Their forms, their chemistries, they are testimony, indelible testimony of the world in which they lived. A world they carry within them forever. There's this thin layer of sediment at the bottom of a lake in Canada, Crawford Lake near Toronto. It could become the official marker for our time. The golden spike for the Anthropocene. The idea is to mark where human activity became the main force shaping the planet. That spike would go into the lake's mud, which is finely layered. And the year 1952 is clear in those layers. That year left a signature all over the world: plutonium. From the fallout of atmospheric nuclear tests, it's an element that didn't exist here before we made it. And it settled everywhere, in ice, in ocean sediment, and in the mud of Crawford Lake. It marks when human technology could change the planet's chemistry in an instant. That's the work of the Anthropocene Working Group, scientists asking a big question: have we left a geological legacy so distinct it starts a new epoch? The evidence says yes, and it's written in materials never seen before in Earth's history. You can walk a shoreline now and find them, tiny, colorful pieces. Microplastics, these synthetic polymers, are in sediments everywhere now, from deep ocean trenches to remote mountain lakes. They don't biodegrade, they'll fossilize. Geologists in the future will find these petroleum-based particles in layers from the mid-20th century onward, and alongside them, new minerals. Crystals that formed naturally but also entirely new forms, like crusts on smelted slag, or the crystalline compounds in electronic waste. There's also a sharp global spike in heavy metals. Lead and mercury, traces of the Industrial Revolution locked in ice and peat, and a big shift in the nitrogen cycle, visible in isotope ratios from synthetic fertilizers. These are the markers of the Great Acceleration, the period after 1950 when human population and consumption and technology surged. Our signature isn't subtle. It's a simultaneous pulse of new chemistry in every archive on Earth. The scale and speed are what set it apart. Take the Paleocene-Eocene thermal maximum. That ancient global warming event, it saw a massive carbon release over about 5,000 years. The total amount was huge, but the rate was a slow geological seep compared to now. We're releasing carbon from fossil fuels at least 10 times faster. The carbon dioxide curve in modern ice cores isn't a gentle rise, it's a near vertical line. A spike compressed into decades. Past events were driven by the planet's own systems, volcanoes, methane. Ours is driven by one species consciously mining and burning carbon that took millions of years to store. The rock record has no precedent, so where will future scientists look for the start of this layer? Candidate sites are being studied globally. Each one holds a pristine record of that mid-20th century turn. Crawford Lake's layered sediments are a top contender, but there's also coral in the Caribbean, its growth bands capturing the exact year of the plutonium spike. There are Antarctic ice cores where the radioactive layer is perfectly preserved, and stalagmites in caves, their calcite holding the chemical imprint of changing air. These sites are being judged for the clarity of their signal, for the moment they freeze in time. One of the most telling preludes to this layer is already visible. In glacier ice, scientists find a blanket of soot, a black carbon layer that starts in the late 1700s and thickens through the 1800s. That's the atmospheric dust of the coal age. The exhaust of steam engines and early industry. It settled on ice sheets and peat bogs across the northern hemisphere. It's the first global smudge of the industrial world. A sooty preamble to the sharper, more complex signature that came later. This leads to a personal thought. We are all participating in writing this chapter. Every piece of plastic that lasts, every molecule of excess carbon dioxide, every altered nitrogen cycle, it's all part of the stratum we're making. The Anthropocene layer isn't an abstract idea. It's the physical reality of our collective existence being deposited now. When a geologist 100,000 years from now examines a core sample from our time, what story will they read? Will they see the layer of a species that reshaped its world briefly, then found a balance? Or will they see the start of a much longer, more unstable shift in the planet's story? The rocks of the deep past hold warnings and examples of resilience. We are the authors now. What comes next in Earth's autobiography is for this moment being written by us. A laser beam, thinner than a human hair, vaporizes a microscopic spot on a fossil shell. A mass spectrometer identifies the trace elements in that instant, dozens of them. This is the quiet revolution happening in a modern geochemistry lab. The rock record isn't just observed now, it's interrogated at the atomic level. The tools we have today are technological detectives. They let us read Earth's autobiography with a precision that would have been science fiction a generation ago. One of the most powerful tools is the synchrotron. It's a massive, ring-shaped particle accelerator. It produces intense X-ray beams. Scientists can place a tiny sample there. A sliver of dinosaur bone, a speck of ancient clay, in the path of that beam. The X-rays pass through and interact with the atoms inside. The resulting pattern creates a detailed elemental map. It shows exactly where strontium or iron or lead is concentrated, inside a fossilized cell. It's like creating a chemical photograph of a moment that's millions of years old. It reveals diets, environments, even causes of death, without ever damaging the specimen. For reading the long, continuous stories in sediment cores, there's X-ray fluorescence core scanning. Imagine a deep sea core, a cylinder of mud 10 meters long, placed on a conveyor belt. An X-ray scanner moves down its length, millimeter by millimeter. It reads the elemental composition continuously. It produces a high-resolution graph, changes in titanium, calcium, bromine, over hundreds of thousands of years. All without cutting the core open. This non-destructive analysis preserves the archive for future generations of scientists with tools we haven't even invented yet. Perhaps one of the most elegant breakthroughs is clumped isotope thermometry. It sounds complex, but its power is simple. For decades, scientists estimated ancient temperatures from oxygen isotopes in minerals like calcite. But that signal was a mixture, temperature and the composition of the water. It was ambiguous. Clumped isotope analysis cuts through the noise. It measures how often the heavy isotopes of carbon and oxygen bond together. They clump within the crystal lattice of the carbonate mineral. This clumping is controlled almost exclusively by temperature when the mineral forms. Nothing else. So from a single fossil shell or a vein of calcite in a cave, researchers can now read the actual temperature of the water to within a degree or two. From tens of millions of years ago, it's a direct paleothermometer, finally separating the climate signal from the background noise. These tools have settled fierce debates. The controversy over the dinosaur-killing asteroid was largely put to rest by neutron activation analysis. It could detect iridium at concentrations of a few parts per billion. Finding that global spike of extraterrestrial iridium in the clay layer was the key chemical fingerprint. It pointed squarely to an impact. Later, advanced imaging like scanning electron microscopy revealed the shocked quartz and microtectites in that same layer. The jury reached a verdict because the technology could see the evidence. The workflow is a marvel of modern science. Follow a drill core from the International Ocean Discovery Program. On the ship, it's scanned and described. Sections are split open, revealing the striped history. Samples are taken for microbiology, for chemistry, for paleomagnetism. In labs across the world, those samples undergo a battery of tests. CT scanners peer inside concretions to reveal perfectly preserved fossils. Ultra-high-resolution mass spectrometers measure isotope ratios with incredible precision. LiDAR maps from aircraft and satellites reveal vast geological formations. They show how a river channel migrated or a coastline shifted over epochs. This technological leap expands our vision into deep time. It transforms a dark stripe in a cliff from a simple layer of rock into a rich, dense chapter. We're no longer just guessing at the past, we are measuring it atom by atom, pixel by pixel. The sophistication of this detective work asks a quiet question. As our tools grow sharper, what deeper truths are waiting just beneath the surface to be read about our planet's fragile, resilient history? The only full-scale experiments on planetary climate change have already been run by Earth itself, and they're preserved in the rock layers we've been looking at. That's why paleoclimatology isn't just about the past, it's a vital tool for the future. These fossilized disasters are our essential data. They're the real-world tests we have to check our climate models against. Without them, our projections for the next century would just be theory. With them, we have a library of outcomes. We can see how the system actually responded when it was pushed. This work is done by climate modelers who focus on deep time. They take evidence from events like the Paleocene-Eocene thermal maximum or the End-Permian extinction. They feed that data into sophisticated computer simulations. That process is called data assimilation. It means using the past to constrain the unknowns we have now. The PETM, for example, tells us exactly how much the planet warmed from a massive, rapid carbon release. By matching their models to that known outcome, scientists can refine a crucial number: climate sensitivity, how much warming you get for a given increase in CO2. The rocks provide the answer key. These ancient periods become climate analogs, windows into possible future states. The Pliocene epoch, 3 million years ago, had CO2 levels similar to today's. And the models, when they're calibrated with Pliocene data from corals and soils, they consistently show a world several degrees warmer, with sea levels significantly higher. Then there's the high CO2 world of the Cretaceous, the age of dinosaurs. It shows a planet with no polar ice caps and a dramatically different circulation of the atmosphere and ocean. These aren't fantasies, they're data-driven reconstructions, scenarios written in stone. The lessons from these archives are specific and sobering. First, the speed of recovery. From hyperthermal events like the PETM, the planet's systems took about 170,000 years to return to normal. That recovery time is dictated by the slow, grinding processes of the geological carbon cycle. It's a timescale that dwarfs human civilization. Second, the lessons of tipping points. The rock record shows clear instances where ocean circulation switched states abruptly. When freshwater caps shut down heat transport, like what likely happened at the start of the Younger Dryas, these are non-linear changes. The system doesn't always respond smoothly. It can flip. Third, and most stark, are the thresholds for mass extinction. The End-Permian event shows us what happens when carbon emissions are both enormous and geologically rapid. It gives us a boundary condition, a line in the sand that, if crossed, leads to the irreversible restructuring of the biosphere. We're not near that line yet. But the rocks define where it is. Paleoclimate data directly reduces our key uncertainties. It helps us understand cloud feedbacks. Did ancient warm worlds have more clouds that reflected sunlight or fewer? The sediment records hint at the answer. It critically informs carbon cycle feedbacks. How stable are the vast reservoirs of permafrost carbon and undersea methane hydrates when the planet warms? The isotopic signatures from past warming events suggest these reservoirs can and do release their carbon, but the rate is crucial. Our current release from burning fossil fuels is far faster than most natural precedents. A concrete example is how PETM research transformed modern models. For years, climate simulations struggled to replicate the full warming and acidification seen in the PETM rock layers. They were missing a feedback. The paleo data insisted the warming was greater than the models predicted. That forced modelers to re-examine the representation of carbon cycle feedbacks in their code. Like the release of carbon from warming soils, that improvement, pioneered by studying that ancient event, is now built into the latest generation of models used by the IPCC. The past taught the models to be more accurate, so when you look at a cliff face or a piece of ancient coral, see it for what it is, a crucial guidebook. The only one we have for navigating a future of unprecedented change. These stone archives aren't silent, they're speaking. They're telling us about sensitivity, lag times, and points of no return. Our task is to listen, to translate that ancient language into wisdom for the path ahead. That dust in the Gulf of Oman, it's from 2400 BCE. That's when the Akkadian Empire fell. It had unified Mesopotamia. For a long time, people thought that was just politics, a failure of leadership, but then they pulled up a sediment core from the Gulf. And there was a layer of dust, wind-blown dust, dated to exactly that time, and the dust came from the north, from the empire's heartland. It was the sign of a mega drought. So severe it turned farmland to desert. It shattered the civilization. That's historical climatology. It puts the stone record together with the human one. You read the tree rings, the ice layers, cave formations, alongside the ancient tablets, the fallen walls. The evidence is precise. In those Gulf cores, the dust particles match northern Mesopotamia. This wasn't a local dry spell. It was a regional shift, lasting maybe 300 years. In Syria, the archaeological record shows a dramatic depopulation. The great city of Tel Leilan was abandoned. Soil samples from its ruins show a thick layer of wind-blown silt. No pottery shards, nothing from human habitation. The land was buried. For the Akkadians, their world didn't just get drier, it blew away. This pattern repeats. You see it with the Sea Peoples. They raided the eastern Mediterranean around 1177 BC. Their origins are a puzzle, but there's a climate clue. Tree ring records from Anatolia, modern Turkey, show a severe, prolonged drought right before they appeared. The idea is that drought crippled inland societies, caused famine and instability. That pressure may have triggered migrations, displaced groups moving toward the coast. They took to ships, became the raiders who challenged Egypt, who toppled the Hittite Empire. The trigger was ecological, recorded in the width of tree rings. And then the opposite, benevolent climate can fuel golden ages. The Roman warm period, from about 250 BC to 400 CE, stable, warm, wet weather across the Mediterranean. Grape cultivation spread north into Britain. Alpine passes stayed open year-round. That aided trade, military movement. This climatic dividend meant agricultural surplus. Economic stability. It provided the environmental confidence that underpinned Roman expansion. The prosperity wasn't just political genius, it was written in the growing seasons. But the climate always turns. Some of the most direct links come from ice, volcanic fingerprints. In the year 536 CE, the historian Procopius wrote about a strange dust veil. It blotted out the sun. He described a year without summer, frosts in August, crop failure, famine. For a long time, that was just a story. Then, ice cores from Greenland and Antarctica showed the cause. A massive sulfate spike, dated to that same year, evidence of a colossal volcanic eruption, probably in the tropics. The aerosol veil cooled the planet for over a decade. Tree rings worldwide from that period show almost no growth. This single event, frozen in ice, triggered pandemics, mass migration, political upheaval from Scandinavia to China. It was a global climate shock that rewrote history. Societies faced these shocks with different fates. In the American Southwest, the Hohokam culture built over 1,000 miles of irrigation canals in the Arizona desert. A marvel of engineering, but when a prolonged megadrought hit in the 1300s recorded in the tree rings there, the canals ran dry. The social complexity needed to maintain the system fractured. The Hohokam dispersed. In Greenland, the Norse settlements were established during the medieval warm period. Then the Little Ice Age descended. They were stranded. They clung to European farming practices as the growing season vanished. Meanwhile, the Inuit, adapted to the Arctic, thrived. The Norse starved in a cold they could not or would not adapt to. There's a stark case in Central America, the classic Maya. For centuries they flourished, built towering pyramids, vast cities. Then, in the 9th century, it collapsed. The timeline of abandoned cities was clear, but the reason was debated. Then scientists analyzed a stalagmite from a cave in Belize. Its oxygen isotopes recorded rainfall history. With seasonal precision, the story was undeniable. A series of intense droughts, each lasting several years, struck between 800 and 930 CE. The droughts correlated exactly with the dates carved on the last monuments in the major Maya cities. The political structure depended on maize agriculture, on royal promises of rain from the gods. It could not survive the failure of the skies. The jungle reclaimed the cities. But the cave stone remembered the exact years the rains failed. It forces a reflection. We often see history as a saga of kings and battles and ideas. But the rock and ice show a deeper current. The slow, powerful pulse of the planet's climate system sets the stage. It creates the abundance that lets empires rise. And it delivers the drought, the unending winter, the poisoned rain that tests their foundations. The question isn't whether a society will face an environmental change. The stone record guarantees it will. The question is about resilience, the flexibility of a society's institutions, its technology, its cultural knowledge. When the climate shifts, as it always does a culture have the capacity to change with it, or does it cling to the memory of a world that no longer exists? The dust in the Gulf, the narrow tree ring, the sulfate spike in the ice, they're more than data points. They are the physical echoes of that moment of reckoning. When the environment writes a chapter of the human story in stone, those same layered rocks that tell Earth's story there on another world. In Gale Crater on Mars, the Curiosity rover sends back pictures. Towering cliffs with cross-bedding, they look exactly like sedimentary deposits here, formed by wind and water. It's not just a landscape, it's a library. A library that hasn't been opened. Planetary geologists are the translators now. Their first tool is orbital spectroscopy. Satellites orbit Mars and scan the surface with light. Different minerals absorb and reflect specific wavelengths. From hundreds of kilometers up, they can map clays that only form in persistent water, or salts like gypsum and halite left behind from evaporating lakes. These mineral maps are the first chapters of Mars's climate autobiography. They show a planet that was once profoundly wet, river valleys, deltas, maybe even a vast northern ocean. The evidence for that ancient ocean is written in the landforms. Along what might have been shorelines, researchers have identified deposits they think came from mega-tsunamis. Enormous waves, possibly from asteroid impacts into that lost sea. The deposits show characteristics of backwash chaotic boulders and sediment carried inland, then dragged back out. If confirmed, these features aren't just geological curiosities. They're the fossilized splash marks of a climate disaster. A sudden, violent event recorded on a world without plate tectonics to erase it. This work is called comparative planetology, using Earth as a reference book to interpret other worlds, and the most powerful lesson comes from Venus. Its surface is a scorching hellscape, hot enough to melt lead under a crushing atmosphere of carbon dioxide. That's the ultimate runaway greenhouse effect. Geological evidence suggests Venus may have once had oceans, but something went wrong. As the sun grew brighter over billions of years, Venus's oceans may have started to evaporate. Water vapor, a potent greenhouse gas, thickened the atmosphere, trapping more heat. That evaporated more water. A positive feedback loop spiraled out of control until the oceans were gone, boiled into space. The geology of Venus's surface, reshaped by volcanism, might still hold clues to that transition. It stands as a dire, silent warning in our solar system. A testament to how a climate system can tip into an irreversible state. So what would we look for in Martian rocks to read its specific climate catastrophes? The first clue is in the air or the lack of it. Mars has a very thin atmosphere, but its rocks might explain why. We'd search for specific isotope ratios. A heavier form of argon compared to a lighter one. In a thick atmosphere, lighter gases escape more easily into space over time. If Martian samples show a high ratio of heavy to light argon isotopes, that's evidence Mars once had a much denser atmosphere that was stripped away. The same process applies to water. Hydrogen in water comes in light and heavy forms. If the remaining water ice at Mars's poles is heavily enriched in the heavy hydrogen, it means the planet lost a tremendous amount of its original water. The lighter hydrogen escaped, leaving the heavier behind. Curiosity has been doing this detective work firsthand. It drills into those layered rocks in Gale Crater. It heats the powdered samples in an onboard lab, sniffing the gases released. It's found complex organic molecules, the broken-down remains of ancient carbon-based chemistry, and it's identified minerals like clay and sulfate salts in a specific sequence. At the bottom of the mound, clays that form in neutral, potentially habitable water. Higher up, salts that form as water evaporates and becomes acidic. That vertical sequence is a climate record. It tells of a lake that existed, then began to dry out and sour. A chapter of environmental change, maybe spanning millions of years, read from a single hillside on another planet. This changes our perspective on Earth's own rock record. It's no longer just our local history, it's a decoder ring. The principles we've learned here, how to read the chemistry of extinction layers, the sedimentology of ancient floods, the isotopes of lost atmospheres, they're universal. They're the tools for reading the stories of other worlds. When we look at the stark, layered cliffs of Mars, we're not looking at an alien wasteland. We're looking at a familiar language, one written in sedimentation, mineralogy, and chemistry. The story is different. The loss of an ocean, the thinning of an air, the quieting of a world. But the grammar is the same. Earth has taught us how to read it. Our planet's turbulent history is the key to understanding the fates of others, and in doing that, we might finally answer a profound question. In this vast and silent cosmos, is the story of climate disaster, of flourishing and failure uniquely ours, or is it a common chapter in the biography of planets? The drill bit that cuts for coal can also cut through a page of Earth's history. That's the tension. Looking for resources, we keep finding the archives that warn us about using them. Mining road cuts, they open these pristine rock sections, a fleeting window into deep time, but once that layer is quarried away, the record is gone. So there's a movement now, Geo-Conservation, protecting key geological sites like their museums, because they are. The most important sites have a name. Global Boundary Stratotype Sections and Points, GSSP, they're the official golden spikes, the precise locations where one epoch is defined against another. The rock layer at Meishan, China, the one that marks the End-Permian extinction, that's one. It's a place of pilgrimage. Protecting it isn't about locking away a rock. It's about preserving the primary evidence, the original text of a planetary event that reshaped everything. Future scientists with tools we can't conceive will need that exact layer. Our stewardship now is a gift to their understanding, and that responsibility extends. It's also about communication. Climate scientists who read these archives face a challenge. How do you convey the lesson of 100,000-year recovery from a warming event without triggering despair or detachment? The timescales are so vast they can feel irrelevant. The key is to bridge deep time and human time, to emphasize that the planet's full recovery is slow, but the impacts of rapid change on our societies, our agriculture, our coasts, those unfold within lifetimes. The rocks don't offer a prophecy, they offer a spectrum of possibilities based on the laws of physics and chemistry that are still in effect. communicating this is an ethical act. Translating the stone ledger into a language of risk and resilience, so choices can be informed. We've already lost chapters, critical outcrops lost to urban development, dams, unchecked mining. A limestone cliff in a European quarry, a perfect record of Jurassic ocean temperatures, might now be ground into cement. Once it's gone, no satellite image can replace the physical sample for new analyses. So there are projects creating digital twins, laser scanning, photogrammetry, building three-dimensional, millimeter-accurate models of fragile outcrops. These digital archives ensure that even if the site is lost, its geometry survives. But it's a backup, not a replacement. The rock itself holds chemical secrets future technologies may unlock. This leads to a concept of scientific heritage. These layered sequences are part of humanity's shared heritage. Like an ancient library, they contain the story of our planet, the context for our existence. Their value isn't in ore or stone, it's in information. Protecting them is an affirmation that some knowledge is irreplaceable and must be held in common trust. So what's our duty, having learned to read this autobiography? The rocks present a moral imperative, twofold. First, to be careful students, to protect the pages of this stone book so the learning never ends. And second, to be mindful actors, to use the wisdom of past climate disasters not as a script for our future, but as a map showing the dangerous terrain. The fossils, the isotopes, the ash layers, they're not just curiosities. They're the accumulated memory of a living planet, a memory that reveals our present moment not as an isolated point, but as a consequential sentence in a very long story. The question is how the next line gets written. The rock layers are a conversation across time, from the Permian seas to Snowball Earth, from an asteroid impact to a supervolcanic winter. Each event left a signature, a chemical whisper, a fossilized sigh. We've learned to listen. These fossilized climate disasters are ancient history, but they're also a library. A stark library of warnings written in mineral and isotope. They show a planet that's dynamic, powerful, often violent in its changes. That library teaches a few core lessons. The first is resilience. Life and the planet's systems have recovered from unimaginable shocks, but the key word is time. Recovery operates on geological clocks. Hundreds of thousands of years, a scale that dwarfs human civilization. The second lesson is the tipping point. The rocks show that climate systems don't always change gradually. They can flip abruptly from one state to another. A freshwater cap on the ocean, a methane release, a veil of volcanic ash, any of these can trigger a cascade. It reshapes the world. The third lesson is interconnectedness. A volcanic rift in Siberia alters the chemistry of the entire atmosphere. The closing of the seaway in Panama helps build ice sheets in the north. The ground, the air, the water, they're in constant dialogue. Now we're writing a new layer, our layer, the proposed Anthropocene. For the first time, a single species is the primary geological force. Leaving a global signature of new materials and rapid chemical change, the lessons from the past become our guide. They're the only real-world experiments we have. They show the sensitivity of the system, the lag times in response, the boundaries we have to understand. The rocks make it clear. Climate change isn't an abstract future concern. It's a geological force, the same kind that carved the chapters we've just read, and we are now reckoning with it. When you see a layered cliff, a canyon wall, a simple stone, see it for what it is. A page in an epic autobiography, a repository of deep memory. That perspective fosters a quiet reverence for the planet's story and a firm support for the science that reads it. Paleoclimatology is the bridge between the deep past and the urgent present. It turns the stone archive into a map for navigation.